Good morning, scholars. Today we are going to start our new subject or Unit 8 on circles. What I would like for you to do right now is grab a blank piece of paper. In addition to that, besides having your own little math companion, I want you to grab some markers if you have them, colored pencils, anything like that. It's going to help highlight some information when we go over some definitions. In addition to that, a couple pencils, things like that, maybe some pencil sharpener, something along those lines. Outside that, probably just use a couple pieces of paper and pretty much our pen and pencils. If you do have it, good idea is to have your compass out as well because we're going to be drawing a couple circles. So please pay attention and let's get started. So let's start off with just first labeling our paper down. What we're going to have here is our circles unit, unit 8. If you happen to have a spiral notebook, that would make this a little bit more organized for you as well too. It's nice to have everything grouped together since we don't have like a notes packet. First thing that we're going to do is basically define what a circle is. We've all seen circles before. We can all pretty much describe them in our own words, but the main idea, the main focus here is going to be um, is this term equidistant, which we're going to apply to our radius and our diameter. But essentially, the way that you can define a circle is just going to be a figure where all points are equidistant, meaning equal distant, equidistant from the center point. Cool. So a figure where all points are going to be equidistant from the center point. One thing to note as well when we're talking about circles, circles don't necessarily have sides. The whole idea is that you have like an infinite number of individualized points going around this center point. So normally we quantify that as like 360 degrees to go around in the circle, but there's essentially like an infinite number of points actually available in the circle. And that goes to that whole notion of like if you're trying to measure something with a ruler, like what's the value of something in between the 2 points that are marked down. With a circle, you just find more and more points individual or atomized as you go down. So infinite number. We have we have three specific terms that we're going to touch on. You might remember back from middle school, but they're going to be our radius, our diameter, and our circumference. The first one we're going to work with is going to be our radius. And our radius we can describe as a segment which connects the center point to the perimeter of a circle. A segment which connects the center point to the perimeter of a circle. You can also call the perimeter of a circle the circumference, but since we haven't touched on that term yet, I'm just going to use the word perimeter. Next up is going to be our diameter. See that word meter in there for measurement, old school Latin. I'm going to say a straight line which passes through the center point and when it passes through the center point, it's going to end up hitting all the endpoints on the opposite side. So your diameter is going to go from one point to a point directly on the opposite side, and the way that it goes directly on the opposite side is going to go through the center. The diameter is basically going to cut a circle in half as well too, and then you have a semicircle, or like an orange slice, say. So for our definition, a segment which connects the center point to the perimeter of a circle. All right, next up, our last one's going to be the circumference. Circumference is essentially our perimeter. Your circumference is going to be the distance around a circle, which is the same thing as like the perimeter. All right, so next thing that we're going to do is essentially describe these in an actual visual example. So what we're going to do here is I want you to take your compass if you got it, and we're just going to draw a circle. The measurement is up to you. Basically, the way that we're going to design this, we're going to make sure our finger's in the center of our circumference or our compass, and we're going to just find a point. This point of measurement that we're going to use, or if you're using one of those pointy compasses, the distance you expand it, it's going to be equivalent to your radius because you're just going around from that center point. If you do not have your compass, you can always grab like a soda can, preferably one without sugar, and draw around the bottom of it as well. Or if you got like coffee can lid, something like that, or a cup, just go around the bottom or the base. So we're going to draw a few things here. First, we're going to take our markers. Let's say color green. We're going to go around our circumference. It's a super cool video online if you go to YouTube. It's something along the lines of mathematicians drawing circles. And there's a short documentary about chalk. That's pretty cool. It's a special type of chalk from Japan. Most mathematicians use to draw perfect circles. It's pretty impressive. All right, so next up we're going to do is our diameter. Our diameter, as we mentioned, goes through basically our center point. Going to be our diameter. And the radius is going to go from that center point to our perimeter of our circle. All right, so just to note, these angles here are going to be random. You don't have to draw them perpendicular or anything like that at all. So we're going to start first off with what's called the equation of our circle. Normally, if you want to quantify a circle, we try and figure out how large it is by its circumference. That's visually how we would see a circle, like how big it is or how small it is. The equation to calculate the circumference, though, is going to be based upon the radius. There's an equation for the diameter, but you have to consider that the radius is essentially half the length of the diameter. So if you have the radius, you can calculate it back and forth. So what we're just going to jot down in our notes here is to quantify a circle, we rely upon measuring the length of a radius. So to quantify a circle, to quantify a circle, we rely upon measuring the length of the radius. And just to remind you, once again, our radius is going to be essentially from the center point to the exterior. All of our radiuses in a circle are going to be identical. So I'll go from the center. So what I'd like for you to do is put down another dot. We're going to write our equation here, but I'm going to give you the visual explanation of how we actually come about with our equation. Essentially what deems our postulate in a way. So what you do is grab a straight edge, and we're going to make a line here on the left side. We're going to just try and draw it perpendicular, almost like we're making a graph. Then we're going to make a circle on this figure. Using my compass, I'm going to use the number 2 hole, so it's not too large. But basically, just to make a circle, doesn't matter where it is. Just you want to make sure your center of your compass is right on the origin. Origin being 0, 0. We want to come around and just draw this figure out. Make sure if you're going to lift your hand up, you're going to put your point back in the same circle, and once again your other sides of your compass are different numbers. So you want to stay in that same exact number 2, number 4, or whatever spot. Alright, next thing we're going to do is draw a point on our line, or sorry, a point on our circle, and that's going to help us form our radius. To do this, we're going to go from our center point and out. Make sure your point of your pen or pencil's on the origin and not the ruler itself. You need that extra space. We're going to label our radius R. And we're going to have our origin point of O. That's going to be at 0, 0. And what I'd like to show you here is essentially the idea, the measurement of a circle. We're going to add a triangle here with our dots. And if we come down and intersect here, we're going to have a 90-degree angle. The way that we go about figuring out the radius, say if we don't have a compass and if we only have, say, the coordinate plane, we can use the distance formula. But one thing we've seen is that your distance formula, if we create like a right triangle, is that it's just the x measurement and our y measurement. Like we did, our distance formula is the chains of x squared plus the change of y squared. Essentially, our equation for a circle is going to be very similar. What I'd like for you to do next is going to be taking that same circle measurement you used. Once again, I used the number 2, up to you. However you want to do it, we're going to create another circle. I would suggest to move it towards the center of your paper because we're going to write on the right side of the paper. And make sure that you have a nice little center point drawn out. Usually you want to start with that, so my mistake. You want to put your compass down, draw in the center portion, and then go out. What we're going to do is draw another radius. And now we're gonna name these points. Our center point we're gonna label C. Is typically how it's written. And we're gonna give it an arbitrary location of point HK. HK. You can imagine this being like 0.612 or whatever on your graph. We're going to have HK. Our intersection up here is going to be point P, or the point on our circle, which is often as it's referenced. C for center, P for point. And we're going to label that XY. Next thing we're going to do here is we're going to try and draw, similar to our circle on the right hand side, we're going to draw an estimated right triangle. And if we were to express this as two separate equations, the bottom here would be, our change of x would be x minus h. So x as in our endpoint, or a point on the circle, h as in the point where the center location of our circle is. This here, our y value, would be y minus k. If we were to now go about and create an equation for our circle, our equation itself is going to be expressed in a similar fashion to our distance formula, but we're going to have our change of x squared plus our change of y squared equal to r squared. So this is your formula for creating a circle. There is another version for the diameter, which we'll touch on later this week, but this is the common means that you will see it expressed. What we just previously saw is going to be the equation of our line where we have our various points. Just to kind of reiterate again here, in regards to labeling, we're going to have x and y and h and k paired together. In terms of how it gets paired together, our x and y is going to be the points that are going to be on the exterior or on the physical circle itself, and points h and k are going to be the center points, like the origin, say, or the center of the circle. What we're going to do now is essentially relate this to if we saw a circle on a graph. So what I would like for you to do is either scooching down your piece of paper or on your next page, we're going to do something that looks a little bit like this. What I would like for you to do is essentially, in terms of setting up your pages, we're going to make a little graph on the right hand side of the page so we can numerize everything. If you do have a actual set of graph paper in your house, like myself, we're going to make a nice little graph here. Your graph, essentially, we're going to have points A resting at 0, -4. Point P, which is going to be your point on the line of the circle, is going to be at 0, -1. And as a test at the end, we're going to have point G, 3, -4. The notion here is, since this is circle A is labeled at the middle point of the circle. And then point P is going to be the radius through which we draw our circle. Looking at this graph, since everything lines up nice and easy, we can tell just by counting 1, 2, 3 that our radius has the length of 3. What we're going to do now is essentially set up the proof of that. Just in case, say, one of our points ends up lying in the middle of sections, it doesn't just sit nice and clearly on the coordinate plane. We're actually going to go ahead and prove this. All right, so first thing we're going to do, as mentioned before, if you don't have graphing paper, we're just going to draw a nice example in the top corner of our page. It doesn't have to be perfect, but we want to have it legible. So first thing we're going to do is we're going to label point A, we're going to have point P, and we're going to do it above on the top right there. And our theoretical circle is going to go around that's going to be our little center point. So what I'd like for you to do now is on the left side of your paper, now that we have this circle drawn out, is we're going to have, right, circle A, and we're going to have P. We're going to label these pieces. Origin of our circle 0, 4, sorry, 0, -4, and then point P is going to be at 0, comma, -1. So just counting the distance here, we can see that it's essentially a radius of 3. But to set up an equation, say we got a whole bunch of various numbers here, and we can't just count it so easily, we're going to set up an equation. We saw previously that we had variables hk and xy. Circle A is going to be is like variables hk, and point P is going to be the x and y. So first thing, the next thing that we're going to do is I'm going to go down here and say with point P, as in we're testing point P, we're going to write our equation. So what's the equation for our circle? All right. So our equation for a circle is going to be x minus h in parentheses squared plus y minus k squared equal to r squared. So if we're going to be asked what is the equation of our circle, we're going to do something similar to that notion of y equals mx plus b, where we're going to go ahead and try and get the variables itself and not necessarily all of the values inside. We're going to leave our x and y alone in that y equals mx plus b example, but we're going to get the m value and the b value essentially. So what we can do here is substitute in. We're going to do x minus 0 squared plus y minus our k value, which is going to be -4 squared is equal to r squared. If we just go ahead and simplify everything down here, x minus 0 is just x squared, y minus -4, which is y plus 4, equal to r squared. This right here is our y equals mx plus b variation of the equation of a circle. Right. So next thing we're going to do is go and look at to see what is going to be like our proof for our radius. If we can't just count it nice and easily, what are we going to do to actually find the r value? To go ahead and do that, basically we're just going to set up our equation again. So if we're going to solve for r, or radius, write out our equation again. And then we just go ahead and substitute our values in. So Go up to the top. Our x value is going to be 0. Our h value is going to be 0. That's squared. Y is going to be -1. And we have that minus -4 again. All squared equal to r squared, our unknown. 0 squared obviously is just nothing. -1 minus -4, or -1 plus 4 squared. Here we're going to have 3 squared, which is 9. Then we can go ahead and say square root everything, and we have 3 equal to r. All right, scholars, so just to finish up here, if we are given various points, way that we can go ahead and verify our information is going to be essentially plotting them in relation to this equation. So for instance, if we were told we had another point that may or may not be on our line, say like point G, and it had a value of say 3 comma -4, you can go ahead and insert those values into the equation such that those points for G would be similar to point P, where we inputted them in our X and our Y. HK is going to stay the same because that's going to be our value of legitimacy. That's where we're going to be testing out from. The other thing that we have to do is when we punch in all the values, the way that it's verified or we check our work is that if we go down and we get the same exact radius or the same exact R value, that dictates that they're both on the same line. If you want to test out point G, that's up to you. If we do plot it out on an actual graph though, these values are essentially the same. You can see that counting out of 1, 2, 3 for our radius, 1, 2, 3 for point G. So what you need to finish up for this particular unit to practice this out is I want you to go into your independent practice, which you can find on Google Classroom. We're going to have a handful of questions there. Just as a reminder, if you do not have things like graphing paper, which I don't expect pretty much any of you to have, feel free to do something along the lines of this where we just drew a line. Might be helpful if you try and actually create an accurate graph yourself with little tick marks. That way you can kind of verify or bring validity to these equations and to these statements that we're practicing. Also, if you go on to, if you do want to print it out, go to Google, go to the image option for search, and then just type in graphing paper. If you're going to do that, you'll want to make sure that you get like one that has really tiny boxes, so you can take the image and stretch it down. Um, or in addition to that, you'd like a good idea is that when you go ahead and print it, that you use one of those options like fast draft, so you save a bunch on ink, because there's really no need for any extra detail there. All right. If you have questions about the material, please hit me up. Once again, you can always go back through the video, or they're on Edpuzzle and the YouTube page as well. The only way I can verify that you yourself watched it, though, is through Edpuzzle. So make sure that that's at least where you start in terms of watching it. All right. Until next time. Bye.